Good morning, Year 5. Welcome to today's Science. It's Wednesday, and this morning we're going to begin our new unit of science, all about physical and chemical changes. We're going to move on from the learning we did before half term, all about different states of matter, and we're going to continue now to look at the changes in those states of matter. Today, we're looking at what happens during state change. For today's lesson, you will need a pen or pencil and your science book. That's all you must have. At the end of today's lesson, I'm going to do a little demonstration, not so much an experiment. We're just going to try and sort of demonstrate some of these changes. If you want to follow along with that at home, you can. It's one you'll need to do in your kitchen on your kitchen hob, but must be done with an adult. I've got my serious pointy finger right here. You cannot do this one alone. You have to have an adult do this one with you because it does involve the hob, having the gas or the electric on or whatever. To do that, you just need a saucepan, a lid, and an ice cube. Okay, so saucepan, lid, and ice cube. But we'll get to that later on. For now, let's get going with our title in your book, please. So pause here and include your title, along with your date. The title is What Happens During a State Change? Okay, so your book's looking ready to go. Let's get our minds ready to go by looking at some very important total recall. This total recall is really, really important. This is definitely not skippable. You must do it because we need this learning for today. If we don't know this, we can't learn more. So, what state of matter does each diagram represent? Have a look at the three diagrams. Tell me what state of matter they each represent. Pause the video and have a go. Before I come up with the answers, though, I'm just going to give you a couple of hints, just in case you're listening to me and thinking, I can't remember any of this. I'm looking for either solid, liquid, or gas. Either solid, liquid, or gas. Have another look. Make sure you've got your answer ready. Pause if you need to. Here come the answers. So the first one there is a gas. I can see that that's a gas because the particles within the gas there are not touching each other. They're arranged randomly, moving around randomly. They're filling the container, and that tells me it's a gas. The liquid, okay, the particles are touching each other now. They're closer together, but they're not arranged in an order or structure. They're arranged randomly. That's really important. And the solid, all touching each other, all arranged in ordered rows or columns. That tells me it is a solid. Quick pause though, because I want to just touch on a word I used there and a word we used before half term, and I think it can be a little bit confusing, this word. The word is particle. So the word particle means a tiny amount of something. It's a great word because we can use it in loads and loads of different ways. But because we can use it for lots of different things, sometimes I think it can create a bit of confusion. So in the last page, we used the word particle to actually describe atoms or molecules. These are the building blocks for everything. Every single thing is made of molecules usually. This means molecules means more than one atom joined together. So atoms or molecules. They're so small that it's impossible to see with our eyes. It's impossible to see with a magnifying glass, with a microscope, impossible. The only way you can see them is an incredibly powerful microscope called an electron microscope. But when we look at particle diagrams like these ones on the page here, we're talking about the tiny, tiny molecules that we cannot see and how they are arranged. But the word particles can be used for something like, if you ever see the sun coming through the window and sort of little specks of dust, and yeah, sometimes you might say, oh, little particles of dust, but they're made up of many, many molecules. And when we're looking at salt last half term, you could say that there was the grains of salt, the crystals of salt, you could say that they were particles, but it can get a little bit confusing because that's very, very different to the molecules. It's the molecules that are in the straight ordered rows. Clearly, when we have a teaspoon of salt, the little grains of salt that we can see with our eye, they're not in ordered rows, are they? They're just in a little pile. We must remember that a grain of salt will contain lots and lots of those molecules. It's the molecular structure, the molecules that are in those nice, neat ordered rows. In fact, prepare yourselves, amazing fact coming up. 1 grain of salt like that would contain, well, how many do we think of these molecules, these tiny, tiny, tiny molecules of, in this case, salt or sodium chloride? How many sodium chloride molecules would be in one? Well, I'll tell you, it's amazing. 1 billion billion. So not just a billion, but a billion billion. huge amount of these tiny particles, and that tells you how tiny those are. So just separate those. So when we're looking at salt, when we're seeing a grain of salt or a grain of sand in our hand, we're not seeing the red dots in this diagram down the bottom. Okay, those are the molecular structure of the salt that we're seeing in that diagram there. Okay, I'm going to clear that one up. Right, let's get some vocab here going in our description of a experiment that we did before half term. I'm trying to say it without giving away the answers. So let's read it in completely with the blanks, and then we'll try and see how we're going to fill them in. Salt is a something solid. This means you can dissolve it in a liquid. In this experiment, salt is the something, water is the something, and together they create a something. And then I've got the 4 words down there that we can fill the gaps with. So salt is a something solid. That means you can dissolve it in a liquid. Choose the one that you think is right, fill in the gaps. Pause the video and have a go. Okay, here come the answers. So salt is a soluble solid. This means that it can dissolve in liquid. Okay, this means that those grains of salt can dissolve in liquid. This means that you can dissolve in liquid. In this experiment, salt is the solute. That means it's the soluble solid, the solid that's dissolving. The water is the solvent. That means it's the liquid that the dissolving is happening in. And together they create a solution. Okay, one more, still on the total recall here. In this mixture of water, salt and sand, how can we separate the different substances to create pure substances? So we want to go to pure. So to go to a pure substance, we want just one substance. So salt water, not pure. That's a solution of salt and water. Here we want to separate them. So I want to have just the salt and just the sand. Which process did we use for each? Pause and see if you can remember. So to get the salt out, we used evaporation. To get the sand out, we used filtration. So sand is an insoluble solid. That means that sand does not dissolve in liquid. So that means that to remove it, we can use a filter. So a filter allowed the water to pass through, but didn't allow the grains of sand to pass through. So we could remove the sand that way. Salt was different, wasn't it? Because salt is a soluble solid. That means it can dissolve in water. So in order to recover it, we have to evaporate off the water. We have to use evaporation to remove the water, and we're left behind with the salt. What happens to the water? Well, that is what we're going to learn about today. Right, let's go through these states of matter then. I'd like you to copy and complete this table into your book. I'll put it in files. If you do have a printer and you prefer to print it, you can do. It will be in files. I'm going to talk you through it, and we can pause at the right moment to fill in the diagram. So along the left, I've got the different states of matter. The first column we're completing is how close are the particles? How close are the particles? What do you think? So in a solid, they are touching each other. The particles are in contact with each other. That's the same in a liquid. Both of those, they are going to be touching each other. In a gas, this is different. The particles in gas are spread apart. They're far apart. How are the particles arranged in a solid, liquid, and gas? Have a go if you want. You can pause the video and try yourself, or you can listen to me. I think in a solid, the particles are going to be arranged in ordered rows and columns. In a liquid, they're arranged randomly, and in a gas, they're arranged randomly. And what about the last one? How much do the particles move? Well, in a solid, it looks very much like nothing's moving, but in fact, the particles within a solid are vibrating, but in position. They are vibrating in position, where they are in their ordered structure. In a liquid, the particles can move past each other. They do move past each other. So in a solid, locked together. in a liquid, the particles can move around past each other. And that's the same in a gas. That is the same in a gas. Pause the video and make sure your table is complete. Right, just tick and fix your answers then. You might have put this into your own words, a little bit different. We said that in a solid and liquid, the particles are touching. In a gas, they're far apart. In solid, the particles are arranged in a regular ordered pattern. In a liquid and gas, they're a random arrangement. In a solid, the particles vibrate in position. In a liquid, they slide past each other. And in a gas, they can move around each other in all directions. So we've now got to decide what makes a solid a solid. How can we define a solid? How can we make sure we know the properties of it? So a solid cannot be compressed. There's no space between the particles. They're fixed together and there cannot be any compression. They do not flow. The particles cannot move past each other. And the particles have a fixed shape. The particles cannot move past each other, so they have a fixed shape. So let's prove this actually. We said that a solid cannot be compressed. There's no space between the particles. So here's a solid. I've got here a large piece of ice, which is a solid object. I cannot compress it. I can't force it to change shape to become more compressed. It doesn't flow. I hold it in my hand and turn it over. It doesn't flow. The particles cannot move past each other. And it has got a fixed shape that cannot be changed by pushing, by pulling, by manipulating it. Our next state of matter is a liquid. So what makes a liquid a liquid? Liquids cannot be compressed. There's no space between the particles. We know they're all touching each other, and we know they're all moving past each other, but there's no space for those particles to fill. It can flow. The particles can slide past each other and move and flow. And lastly, we know it can take the shape of a container, take the shape of the bottom of a container. It will fill the container that it is poured into. So I've got here now a plastic bottle and I've just filled it up with water. So all that's within this plastic bottle then is liquid. And if I squeeze it really hard, I can't compress it. I cannot change the molecular structure inside the bottle of that liquid. I cannot compress the liquid because there's no space between the particles. They're moving around each other, but they are so close together, it cannot be compressed. I've also said that water can flow, so we'll put that to the test, but we know what's going to happen here. The water is going to flow out of the bottle and into the glass. The particles can move past each other so that it can move. It can flow. And we also said, look, it fills the bottom of the container. It takes the shape of the container it's in. Within this glass now, the liquid is in the same shape as the glass because it will spread and it will fill the container. So those are the properties of a liquid. Last one then is here comes gas. What makes a gas a gas? Well, gases can be compressed. There is space between those particles that are moving around so that when I compress it, those particles can move closer together and gas can be compressed. It can flow. Particles are moving all the time in all directions. So just like a liquid will flow, gas will flow as well, but the particles can move a little bit sort of more, so it doesn't flow in quite the same way necessarily as a liquid would. It'll fill the shape of the container, not just the bottom. It will fill the container all the way, as much as you can, as space as there is within the container, it will fill. So let's have a little look at. So I've emptied out my container, emptied out my water, my bottle of water, so that now it's just got some air inside it. It's just got that gas mixture, that gaseous mixture of nitrogen, oxygen, carbon dioxide, argon, some other little bits and bobs as well. But those gases, it's a mixture of gas now within this bottle. So I said that gases can be compressed. So what we expect to happen when I squeeze this bottle? With the liquid inside, I couldn't squeeze it, I couldn't compress it. I've got the lid on tight shut, so I know that the gas can't escape out the top. So I should be able to squeeze this bottle. And I can. I hold it flat so you can see. Look, on this time, I can compress the gas within because it is a gas and not a liquid or a solid. The particles can be moved closer together. I can compress it. And we do this, we hear sometimes compressed air. Divers, scuba divers use compressed air, where air has been squished together to take up a smaller amount of space. We also said that gas can flow, but the problem with air is there's a bit of water coming out there. We can't see the air coming out. Air is a colourless gas, so we can't see it. How can we see that gas can flow? Well, if we think about steam coming off a kettle, we can see that the steam escapes and flows that way. It fills the container. That's difficult to see as well. Within this bottle, that air has filled the container, but again, because it's colourless, we can't see it in any way. If we think about something, like steam, water vapour, perhaps a steam room you get at fancy spas, we can see how the steam fills the entire room. It isn't just kept in one corner, it fills the container that it is in. So those are our properties of solids, liquids and gases. So if we put these to the test then, what are these substances? Are they solid? Are they liquid? Are they gas? Pause the video and see if you can decide which state of matter these 6 are in. So here come the answers. The rock is of course a solid. Yeah? It's a hard solid. It doesn't flow. It can't be compressed, and it doesn't take the shape of a container. It's just a hard rock. Ice is the same. I already showed you that one. Steam, that's going to be a gas. We know that it is water vapour. It moves like a gas. It can be compressed like a gas. It's another way of it's a gas. Helium that's within a balloon, that's a gas as well. It's a very interesting gas. It's less dense than air. That's what makes our balloons lift up. So within the balloon there is helium. So if we sit on the balloon, it can be compressed a little bit. We know it fills the container because it's filling out the whole shape of the balloon there. Now that gold is in solid form. It's it cannot be compressed. It is not taking the shape of a container, and it's not flowing. And the last one, lava, is a liquid, isn't it? Lava flows. Now within these examples here, we can start to see some more about today's learning, because we can start to work out how we've got similar substances in different states of matter. Because heating and cooling changes substances. What happens to substances when they are heated and cooled? If you think about water, what happens to the different forms of water when it's heated or cooled? Well, increasing temperature gives energy to the particles, and this causes them to move around more. So when we increase the temperature, when we heat something up, it gives more energy to the particles within the substance, and that causes it to move around more. So if we take a solid like ice and we heat it, the temperature increases, the particles move around more, and it changes state from a solid to a liquid. We call this melting. This is melting, where we go from a solid to a liquid by increasing heat. If I continue to increase the heat, the water will turn into steam. It will continue to give energy to the particles. They will continue to move around more until they develop into steam. We call this boiling. We call this boiling. But what if I go back the other way? What if I decrease the temperature? If I decrease the energy there, I can go from a gas to a liquid. We call this condensing. condensing. I've gone from a gas to a liquid by cooling it. Gone from a gas to a liquid by cooling, we call it condensing. Now, if I go from a liquid to a solid, again, so I've gone from a liquid, like water, going to a solid, turning water into a solid. How do we do that? What piece of equipment in your house would do that for you? It would be your freezer, because we call this freezing. We call it freezing, moving from a liquid to a solid. I'd like you to copy and complete that diagram in your book, please. So I've got the three states of matter. I've shown them in pictorial form, and I've showed them in a particle diagram. And then I've shown the changes of state of matter between them. Copy and complete that into your book now. So it should look like that, just like we went through with those four key processes: melting, boiling, freezing, and condensing. Right, our final job for today is we're going to look at some examples of state change. I'd like you to copy these state changes into your book and decide what is the state change going on here. When steam is produced from a kettle, which of these four is going on? We put in water in the kettle, turn it on, and steam begins to escape from the top. Is that melting, freezing, condensing, or boiling? Choose that, choose which one, and then explain briefly why. What's happening? What process is occurring? And then do the same for the other four there, please. Pause and complete that in your book. Okay, so time to tick and fix. Did you get the same? Steam from a kettle is boiling because water is becoming a gas. Rain turning to snow is freezing because liquid water is becoming a solid snowflake. And ice cream on a hot day is melting because solid ice cream is becoming a liquid. It's turned from solid form into liquid form. And water forming on the bathroom mirror, this is condensing, where steam, gaseous water, is becoming a liquid when it touches the cold surface of the mirror. Okay, that's enough for our books. I thought before we go though, we'll just take a look at this in practice, and we'll see if we can take water on this journey from solid to liquid to gas through those changes in states of matter.
Okay, so here I am in my kitchen. I've got a small saucepan here, and I've put inside of it an ice cube. I've taken the lid for it. I've actually put the lid in the freezer, just because that kind of improves our condensing a little bit later on by making that as cold as possible. Right, I'm going to put the heat on under there. Again, make sure you're doing this with an adult. I'm going to put that on sort of medium heat. And what am I looking for here? Well, I'm looking for the state change from solid. I've got solid water in this ice cube, and already I'm beginning to see that changing into a liquid. So the temperature change, the temperature increase, is causing more energy in the molecular structure within the ice cube, and that's causing the state change, that the solid ice is now becoming a liquid. Keep your hands out of there. I'll just let that happen. If I could always pick it up by the handle and just move it around a little bit. Make sure that's melting away. As that becomes water, I'm going to turn that heat right down low now. That's now hot enough to continue to melt. So we've gone from solid to liquid. So we are melting. Continue melting for another minute or so as it begins to disappear. The ice cube, that's the wrong word, not disappearing, that's the wrong word. We're definitely not disappearing. Everything is still staying there within the pan. It's just a change of state from solid to liquid. Still a little bit of ice left. Right, now that ice has just about completely turned to water, I'm going to turn the heat up a little bit, make sure it's still lit there, which it is. Now we're going to go for the next change of state, and it's already starting to begin here. I'm going now from water into a gas. That's happening through boiling. The water is boiling, it's turning into a gas. I can see it's turning into gas because I've got bubbles appearing. Bubbles of gas are appearing within the liquid and they're beginning to escape because I can see small puffs of steam happening here. I'm going to pause this here though. I'm going to take that off the heat for a moment whilst I go and grab my lid. So the reason I've got my lid is that now if I continue this boiling process and I put the cold lid on the top, that cold surface, when the gas hits that cold surface, when the gaseous water comes into contact with the cold surface, the temperature is going to change again. It's going to become cooler. So when gaseous water hits the cold surface of the lid, I'm going to go from gas back to liquid. I'll leave that for just a minute or two. Probably only going to take me 20-30 seconds. Actually, yeah, I can already see it. I can see it appearing on the underside of the lid there. And if I wanted to, I could get a little plate or something and just dribble that off there and collect from the lid the water. Okay, there's water on my plate. It's gone back from gas back to liquid here. If I continue to heat this, all of that water is going to turn into gas. Now the thing with gas is it's going to fill the container. So in this case, the container is my kitchen. So all of that gas now is just filling out throughout the whole kitchen. Very difficult for me to retrieve that now. That's kind of gone. I can't get that back. We'll just leave it until we see all of that water change state from liquid to gas. Still a little bit of liquid left. Get it right over the heat until it's all gone. And there it goes. The last of that water then changed state into a gas. Now, if I want to fully complete this process, well, I could take my water and put that plate back into the freezer now for half an hour or so, and then I would complete that cycle, go right back down to ice and refreeze the water. There we are then, those are our different states of matter. We'll continue next week by looking more at physical changes. Bye bye for now, Year 5.